Okay, welcome in. So what we're going to do today is, first of all, cross van der Waals off the list. I think we've discussed that enough. And we're going to consider dipole-dipole interactions for relatively strong dipoles. We're going to consider ion-dipole interactions, and then we're going to wrap up with full charge-on-charge interactions. Stay tuned. So when we considered the Keesom energy a while back, this is the picture we had. We had two dipoles with magnitudes P1 and P2. We defined these angles theta 1, theta 2, and a rotational angle phi, and then a distance between the center of the dipoles r. What we said in this case was that in the Keesom, the interaction energy was less than or perhaps similar to 1 kT. As a result, the dipoles were free to rotate since this was a relatively weak effect. What we're going to consider now is this double D effect, dipole-dipole, where they're relatively strong. This is going to be greater than a kT, significantly so, such that the dipoles are held fixed in place. So the expression that we had in terms of angles is just the answer. We don't need to do the angle averaging that would come from the rotational effect. So what we had for the interaction energy between the two dipoles was a pretty simple expression. The magnitudes of both of them multiplied, 4 pi epsilon 0 and r to the third. Now remember, when we did the averaging, we had to take the second order term of this squared, so it became an r to the sixth. But in this case, we're leaving it r to the third, so it's a bit more powerful. We have this long expression of angles. And I'm going to wrap to the second line, minus sine theta 1, sine theta 2, cosine phi, and then close the brackets. So that's our expression. And what you could notice from this is the maximum value that this could take on would it be if the two dipoles were oriented in the same direction, like this. In this case, the angles theta 1 and 2, realize that's a 2, it should be a 1 and a 2, would both be 0, and so this whole top part would just become a 2, and then the sine of the angle would go to 0. So in this case, the maximum that it can be, so you could say r 0 0, and phi could be allowed to rotate because, of course, since it's being multiplied by these sine terms, the cosine of phi wouldn't matter at all. This would simply end up being 2 P1 P2 over our familiar constants. So that's effectively the maximum that this force can be. And we can be a little bit more quantitative about it. And one of the things we'd like to find out is at what radius does this approach 1 kT. So that's when it would start to fall into the other category of being small, vanishingly small. This is our thermal energy that we compare most things to. And it turns out that that distance is about 3.5 angstroms. So that is a good estimate you can use for this dipole-dipole interaction. If you're less than that, this effect is going to be pretty strong. And if you're greater than this separation distance, then it'll fall off and get pretty weak. Now, a good example of a dipole-dipole interaction is the hydrogen bond. This is a pretty strong interaction between water molecules, for example, since the molecules themselves are pretty short and they have a strong dipole, so they can orient themselves, hold a fixed angle. And again, this is the estimate we use. 3.5 angstroms or less means that something could be participating in a pretty strong hydrogen bond. There's the train. So the next thing we want to consider is the ion-dipole interaction. So we have this full charged ion over here, which we'll say has a charge of Z times E. So this is the valence times the electric charge. So Z could be +1, +2, -1, -2, something like that. It could be an ion, or it could be just a charged group on a larger molecule. And here we have a dipole located a distance r away with these charges like this, forming an angle theta with respect to the separation radius. Now, this ion, we effectively can just say it's like a point charge. The electric field that it's going to have is just going to be Q over 4 pi epsilon 0 r squared. And that gives us most of the answer. The interaction energy tends to just be given as the following. W of r is equal to minus Z times Z, since that's what Q is in our example. The magnitude of the dipole P and the cosine of the angle divided by 4 pi epsilon 0 r squared. All we've done is effectively taken the electric field and added in the contribution of the dipole, and that's what we get here. An even stronger effect, r to the second, means this falls off slower with distance and can act over a little bit larger range. So this is sort of the next most important or a powerful effect in a sense. Now lastly, we can just write down a very simple expression for a charge-charge interaction in which we have two charged objects, Z1 times E and Z2 times E, separated by a distance r. We know what the Coulomb force would be between the two objects. F Coulomb would simply be Z1, Z2, E squared, which is just the charges multiplied, 4 pi epsilon 0 over r squared. And from this, we would also have the interaction energy is the same expression, but over r instead. Now this has to have some direction. Of course, we're sort of ignoring that. This is just the magnitude of the force. So we're also sort of ignoring the sign change here. But of course, we know that if there's opposite signs of the charge, this would be attractive. Epsilon 0 over r. So falling off as only 1 over r, instead of the higher powers we've previously seen, means that this acts over actually a very great distance. In fact, in vacuum, the radius at which this falls to 1 kBt is actually 56 nanometers. So that would be W of R equals 56 nanometers is approximately 1 kT. So if you're closer than that, you can imagine it's much stronger. It's on the order of hundreds of kT, and it's approaching actually a covalent bond between the two charged things, such as ions, sodium and chloride. Now in a solvent, it's a very different story, but really for most of these equations, we've been focusing on vacuum. We only have epsilon 0. We don't have the other dielectric constants of a solvent, of water, of some other medium. So this is very, very strong, comparable to covalent interactions in the vacuum. In the next video, we'll wrap up with some concluding remarks, and that'll be the final part of our interatomic forces series.